Surface integrals. Here we're going to consider integrals over surfaces. Suppose that our surface has a parametric representation by the vector function r. If we integrate over a surface S, and we have some function of x, y, and z, that turns into a double integral of f of r, and then we have the magnitude of the cross product of Ru with Rv. Now remember, Ru is the partial derivative of r with respect to u, and Rv is the partial derivative of r with respect to v. And the reason we do the magnitude of the cross product here is that we are looking at the area of the associated parallelogram. So let's go ahead and take a look at an example. So we have the double integral over the surface, which is the unit sphere, of the function x squared. So we know how to parameterize the unit sphere. In fact, we did this in an earlier problem in another video. We just used these spherical coordinates. Of course, rho is equal to 1. And so the parameterization is x is equal to sine of phi, cosine of theta. Y is equal to sine of phi, sine of theta. And z is simply equal to cosine of phi. And then we need to take the partial derivatives with respect to phi and theta. And then finally, we need to take the cross product of those partial derivatives. Now, we actually did this in an earlier video, so I'm going to save a little bit of time here and just say that this is the sine of phi. So if you want to pause and go through those partial derivatives, I welcome you to do that. There's a little bit of trig identity stuff, mostly the fact that sine squared plus cosine squared is equal to 1. But nevertheless, we can now take this double integral over the surface S of the function x squared ds, and we can convert this into a double integral over the parameterized surface, the sphere, which is now a parameterized surface. And don't forget that theta goes between 0 and 2 pi, and phi is in between 0 and pi. This is the standard limits for spherical coordinates. So theta goes from 0 to 2 pi, phi goes from 0 to pi, and now we are simply going to plug in to x squared, the parameterized value for x, which will be sine of phi, cosine of theta, squared. And then we have to multiply by the magnitude of the cross product of r phi and r theta, which is sine of phi. And then we have d phi, d theta. Now, because our function of theta and our function of phi can be expressed as a product, we can go ahead and pull out the cosine squared of theta d theta here. And then the phi is going to be sine squared times sine, which is sine cubed of phi, d phi. And now these are pretty basic trigonometric integrals. So I'll remind you here that we need to use the half angle identity for cosine squared of theta. And then over here, we just need to do a little manipulation. So we're going to write that as sine of phi times sine squared of phi, which is sine of phi times 1 minus cosine squared of phi. And if I have the integral of that, we're just going to let u equal cosine of phi. Du will be negative sine of phi d phi. And this becomes negative integral 1 minus u squared du, which is going to be negative u minus u cubed over 3, or u cubed over 3 minus u. And then we'll simply put the u back in, which was cosine of phi. Okay, so that integral there, once it's all worked out, is going to be cosine cubed of phi over 3 minus cosine of phi. And then we're going to integrate that from 0 to pi, or evaluate that from 0 to pi. So let me go ahead and get all this out of the way. All right, and then of course this other integral is simply going to be 1/2 theta plus 1/2 sine of 2 theta from 0 to 2 pi. And then we'll bring in this other one down here. So, a little bit of work, but by now these should be fairly straightforward. Here we're going to have 1/2 times 2 pi. The rest cancels out, multiplied by, if we plug in pi, cosine of pi is -1, so we have -1 cubed over 3, minus the cosine of pi again is -1, minus, we plug in 0, we get 1/3 minus 1. All right, so this is pi times, and then we have -1/3 plus 1 minus 1/3 plus 1. And that is 2 minus 2/3, which is 4/3, so we end up getting 4 pi over 3. Now, what about an integral over a surface where the surface is described by a function, let's say z equals g of xy? In this case, we can parameterize this by letting x equal x, letting y equal y, and letting z equal g of xy. So in this case, the double integral over the surface simply becomes the double integral of f of xy, g of xy. And then the ds, you might recall, because we did this in the past, that ds here is this here. So it's the square root of dz partial z partial x squared plus partial z partial y squared plus 1. And I should mention that the surface doesn't have to be z equals a function of x and y. It could be y is equal to some function of x and z, or it could even be x is equal to some function of y and z, okay? So there's nothing special about z equals a function of x and y, except for the fact that normally our surfaces, when given as a function, is usually expressed as z as a function of x and y. So this is the most common, but it doesn't have to be this way. So in other words, if y was a function of h and z, then you would simply replace y here with that function, and then z would just be z. And then in here, you would have the partial derivative of y with respect to x, the partial derivative of y with respect to z, and then plus the 1 there, okay? All right, so let's go ahead and consider an example. So let's evaluate the double integral over the surface, where the surface is given by z equals x plus y squared. X is between 0 and 1, and y is between 0 and 2. And the function is just the function y, okay? So again, we're just going to let x equal x, we're going to let y equal y, and we're going to let z equal this function of x and y, which is x plus y squared. And so the double integral over the surface S of the function y ds becomes the double integral of, well, y is going to just stay y, right? We don't have to change y. And then we do have to multiply by the square root of the partial derivative of z with respect to x squared. Well, that partial derivative with respect to x is simply 1, right? So it's going to be 1 squared. Plus, then the partial derivative of z with respect to y is going to be 2y. So we're going to have 2y quantity squared. And then plus 1. And then dy dx. Y varies between 0 and 2, and x varies between 0 and 1. And just for reference here, this is the formula that I am using. Okay, that's where this came from. So now let's just go ahead and perform the integration. So this becomes the integral from 0 to 1. And we can go ahead and just say dx, right? And then the integral from 0 to 2, and then we have y times the square root of 2 plus 4y squared dy. Okay? All right. So now to finish this integral here is simply going to be x from 0 to 1, which is equal to 1. And then for this other integral, I'm just going to let u equal 2 plus 4y squared. Du is going to be 8y dy So 1/8 du equals y dy. And so this integral becomes 1/8 integral. We're going to have the square root of u du. And then the limits, when y is 0, u is 2. And when y is 2, we're going to get u equals 18. Okay? And so now we just have to perform this integration. So we have 1/8. The integral of u to the 1/2 is 2/3 u to the 3/2 from 2 to 18. This becomes 1/12, 18 to the 3/2 minus 2 to the 3/2, which is 1/12, 18 radical 18 minus 2 radical 2. And the square root of 18, you can pull out a 9, which becomes a 3. And so we have 18 times 3 is 54 radical 2 minus 2 radical 2, which is 1/12 times 52 radical 2. And if we do a little simplifying, we can divide by 4 and get 13 radical 2 over 3. And this is our answer because the other integral, remember, was equal to 1, right? And so when we multiply 1 times the value of this integral, we simply get this answer. Next, let's evaluate the double integral over the surface S of the function z, where S is the surface whose sides are given by the cylinder, x squared plus y squared is equal to 1, which is the graph you see here. X squared plus y squared is less than or equal to 1 in the plane z equals 0, so that is simply the unit circle in the xy plane. And then the top is the part of the plane z equals 1 plus x that lies above the unit circle down below here. So basically we have a cylinder where we are cutting it off at the bottom here, which is z equals 0, right? So the xy plane. And then the top we're kind of slicing with this plane as the top. So if we integrate over that surface, we have to integrate over each one of those 3 surfaces. So we have the integral over the surface S of z ds is going to be the integral, I should be saying double integral, but I think you know what I mean. We're going to have the double integral over the first surface of z ds plus the double integral over the second surface of z ds plus the double integral over the third surface of z ds. So now the question is, do we simply want to integrate using x's, y's, and z's, or do we want to find some kind of a parameterization? So first, let's focus on S1. So if we want to look at the double integral over S1, S1, of course, is this cylinder that you see here. And because it's a cylinder, the easiest way to do this is to do some kind of a parametric representation, right? So on that cylinder, we know that we can parameterize x and y by letting x equal cosine of theta, y equal sine of theta. And we know this because we know that on this cylinder, x and y have to satisfy this unit circle down there in the xy plane. And then, of course, on that cylinder, z is simply going to be z, right? So if we have a point on the cylinder, the z value is just the z coordinate of that point. So what we have here for our r is a function of theta and z. So we have cosine of theta, sine of theta, and z. So then to evaluate this, we need r theta crossed with r z. So first, let's go ahead and find r theta. R theta is the derivative of cosine of theta with respect to theta. That is negative sine of theta. The derivative of sine of theta with respect to theta, which is cosine of theta. And the derivative of z with respect to theta is 0. And then rz is going to be the derivative of cosine of theta with respect to z, which is 0. The derivative of sine of theta with respect to z, which is 0. And the derivative of z with respect to z, which is 1. Okay? So now if we take the cross product of this, we are going to get cosine of theta, sine of theta, and 0. So you can go ahead and find the cross product of these two vectors. And then we're going to take the magnitude of that cross product, which is simply going to be the square root of cosine squared theta plus sine squared theta, which is 1. So r theta rz is 1. That's super simple. So now we just have to take the double integral over our region D. Okay, now we have to describe that region. And then we're going to have the function z, which is actually z. And then it'll be dz d theta. So the key is, what is z in between? And what is theta in between? So just imagine if you are a point on this sliced cylinder here, on the sidewall here of this sliced cylinder, how would you describe the value of z and theta? Well, theta quite clearly goes between 0 and 2 pi because we have to go, all the way around to capture the whole thing. The lowest value for z is, of course, 0. But then the highest value of z depends on where you are, right? So like if you're over here, the highest value of z, might be 2 or something. But if you're over here, the highest value of z is going to be less than that. So how do we know what that is? Well, we know the equation of this plane was up here. Z is equal to 1 plus x. And so z is between 0 and 1 plus x. But that means that z is between 0 and 1 plus the cosine of theta, because in our parameterization, x is equal to the cosine of theta. Okay, so this is going to be the integral from 0 to 2 pi d theta, integral of z dz from 0 to 1 plus cosine of theta. And oops, I cannot do this. I need to keep my d theta over here. And then we're just going to evaluate this. So we have the integral from 0 to 2 pi of the integral of z with respect to z is 1/2 z squared. And that goes from 0 to 1 plus cosine of theta. And then d theta. So let's go ahead and evaluate this. We're going to have the integral from 0 to 2 pi, 1/2 1 plus cosine of theta squared. And of course, when you plug in 0, you get nothing, and then d theta. So we got more integration to do here. So we've got 1/2 integral, then 1 plus 2 cosine of theta plus cosine squared of theta, d theta. And then, of course, we need to use a double angle identity here. So that's going to be 1/2 plus 1/2 cosine of 2 theta. And I think from here, we'll just go ahead and put down the result. Okay, so you get 3 pi over 2. So let's keep in mind that that was the integral over the first surface, S1. We still have to integrate over S2 and also S3. So let's work on those now. For the surface S2, which is this unit circle down here in the xy plane, we know that if you're a point on that unit circle, z equals 0 there. So if we look at the double integral over S2 of z ds, this is going to be the double integral over S2 of 0 ds, and this is equal to 0 because the function, or I should say the z value when you're on that surface is always 0. So integrating over S2 is really simple. Let's take a look at S3. So now let's consider the double integral over S3 of our function. S3 is this region here, or that surface, I should say. Okay, so when we are on that surface, z is equal to 1 plus x. So we can write this as the double integral over a domain D of 1 plus x. And then now we need to do partial derivatives. The partial derivative of z with respect to x is 1. The partial derivative of z with respect to y is 0. And therefore, when we do the square root of partial derivative with respect to x, squared plus partial derivative with respect to y squared plus 1. We're going to get the square root of 1 squared plus 0 squared plus 1, which is the square root of 2. So we'll bring that in here, square root of 2, and then ds. Excuse me, dA. Okay, so now how should we integrate that? What is our domain or our region D here? Well, it's this region, and this is kind of hard to describe using rectangular coordinates. But if you project that down into the xy plane, we can see very easily that the projection down in the xy plane is nothing more than a circle, right? A circle of radius 1, okay? Now, when you're a point somewhere in here, you could have a radius less than 1, right? So the parameterization is just going to be changing over to polar coordinates. I'm going to let x equal r cosine of theta, y equal r sine of theta. Theta, of course, will be between 0 and 2 pi, and r will be between 0 and 1, again, because this down here is the unit circle. And so this integral here becomes radical 2, let's go ahead and factor that out, double integral, 1 plus x becomes 1 plus r cosine of theta. And then don't forget there's r dr d theta. This is when you change over to polar coordinates. 0 to 2 pi and then 0 to 1. And now we just need to compute this. And so this is going to be radical 2, integral from 0 to 2 pi. Let's go ahead and recognize that if you multiply this r here, we get r plus r squared cosine theta. So when we integrate that with respect to r, we will get 1/2 r squared plus 1/3 r cubed cosine of theta, evaluated from 0 to 1, and then d theta. And so this becomes, when you plug in 1, you get 1/2 plus 1/3 cosine of theta. Right? And then when you plug in 0 for r, you get 0. And now we'll go ahead and finish this. So the integral of 1/2 is 1/2 theta. And then we have 1/3 sine of theta from 0 to 2 pi. And you only get something that's non-zero when you plug in 2 pi. Okay? And so if we plug in 2 pi, we're going to have radical 2 times 1/2 times 2 pi, which is radical 2 times pi. So in the end, the double integral over the surface of the function z ds, remember, it's the integral over s1, which was 3 pi over 2, plus the integral over s2, which was 0, plus this one. And so it is 3 pi over 2 plus pi radical 2. Before we go on to the next part of this lesson, let's talk about oriented surfaces. Now, to be able to discuss an oriented surface, we need to make sure we're talking about a surface that has two sides. Believe it or not, there are some surfaces, such as a Mobius strip, which is a single-sided surface, and you can look into the textbook for that. But if we have an oriented surface, a surface with two sides, think about it as like sort of a sheet of paper or something, you could be on either side of this sheet of paper. So if you were on the top side of this, you would have a normal vector pointing upward. If you were on the underside of this surface, suppose you were walking on the underside, you would have a normal vector pointing downward. So if you imagine walking along a surface, this is the upward orientation of that surface. Whereas if you were walking on the underside of the surface, this would be the downward orientation. Now, the next thing we're going to talk about is flux. And when you compute the flux, if you do your orientation incorrectly, you'll get the opposite sign of the correct answer. Okay, because basically these normal vectors, they're just opposites of each other, right? So if you use one instead of the other, your answer will simply be the opposite of what it should be. But we want to make sure we get the right answer. So now we're going to talk about surface integrals over a vector field. Okay, so we have some kind of a surface, and then we have a vector field F, And we want to know how that vector field acts upon that surface. So a way to think about this is, suppose your vector field is talking about the motion of some fluid here in space. And then imagine if you had sort of an invisible surface there. The flux is the measure of how that vector field is flowing through that surface. Okay? Now, if it's flowing tangent to the surface, basically there will be no flux at all. Whereas if it's flowing perpendicular to the surface, you get a sort of like a maximum flux, okay? So the definition here is, if F is a continuous vector field defined on an oriented surface S with a unit normal vector N, then the surface integral of F over S, which we represent like this, is equal to the integral over the surface of the vector field dot product with the unit normal vector to that surface, ds. And this integral is called the flux of the vector field F across the surface S. So we have two ways of finding the flux. One way to do it is when your surface is defined parametrically. If that is the case, then the flux of your vector field over the surface S will be equal to the double integral of your vector field dot product with your RU cross RV vector. Let's do an example. Find the flux of the vector field F of XYZ equals ZI plus YJ plus XK across the unit sphere. So, of course, here we are going to use the spherical coordinates to parametrically define our surface. Let's go ahead and write that down. So, of course, rho equals 1, and we have our standard parametric equations for a unit sphere. Now we need to take a look at our vector function f at r. So our vector function is right here. So we can think of this as f is equal to z, y, x. And now we are just going to plug in these for z, y, and x. Oops, I said x and I wrote a z. There we go. All right, so f of r is going to be z, which is cosine of phi, y, which is sine of phi, sine of theta, and x, which is sine of phi, cosine of theta. So we have our f. Now we just need to get RU and RV and then take the cross product. Of course, that's going to be R phi and R theta. So R phi and R theta. We found these earlier. Let's go ahead and write that down. Okay, so there's R phi, R theta, and R phi cross R theta. Let's simplify R phi cross R theta. You can factor this out, and then cosine squared plus sine squared is going to equal 1. So this last one here is going to simplify to sine squared phi cosine theta, sine squared phi sine theta, and then the last component there will just be sine phi cosine phi. Okay, now we need to take the vector field f, which is right here, and the dot product of that with this here. Okay, so we need to take the dot product of these two things. So f dot u phi cross u theta will be, let's go ahead and go through this. So we have cosine of phi multiplied by sine squared phi cosine theta. That's going to be sine squared phi cosine theta. Plus, then next we have sine phi sine theta times sine squared phi sine theta. That's going to be sine cubed phi sine squared theta. plus, and then lastly, sine of phi cosine of theta multiplied by sine of phi cosine of phi is sine squared of phi cosine of phi cosine of theta. Now notice that these here are like terms. So we have one of those plus one of those. That's going to be two of those. So 2 sine squared phi cosine phi cosine theta plus sine cubed phi sine squared theta. Okay, so this is our vector field dot product with this, which is essentially our normal vector. All right, now we just need to take the integral of this. So we have the double integral of this function. D phi, d theta, phi goes from 0 to pi, and theta goes from 0 to 2 pi. So now we just have to do the integration here. Now, both of these can be separated, and so what we have is the following. Okay, and if you perform all these integrations, which I am not going to do in this video, you get 4 pi over 3. Now, if we wish to find the flux over a surface described by z equals g of xy, we can use this formula. So double integral of f dot ds over s is equal to the double integral of this expression. Now, this expression simply comes from taking the dot product of the vector field with your cross product of your r vectors, but the parameterization is now x equals x, y equals y, and z equals g of xy. So let's go ahead and take a look at this example. Let's recall in this formula that the vector field f is what we are calling p, q, and r, where p, q, and r are functions of x, y, and z. Okay? And then g is this here, right? So z equals g of xy, which is equal to 1 minus x squared minus y squared. That's what g is, at least on this part, this S1, right? This part of the surface, which we're going to do first. Okay? So for us, f is p, q, and r, which is y, x, and z, as defined over here. And on S1, we have the paraboloid z equals g of xy, right here. So let's go ahead and compute the partial derivative of g with respect to x. That's going to be negative 2x. And the partial derivative of g with respect to y is negative 2y. And now this integral over S1 of f dot ds is going to be the double integral of negative p, which is negative y, times partial derivative of g with respect to x is negative 2x, minus q, which is x, multiplied by the partial derivative of g with respect to y, which is negative 2y, and then plus r, which is z, and then dA, and then over our region D. Now, this is actually a problem, isn't it? Because if you look at this carefully, we have a double integral, but we have 3 variables. When you have a double integral, you're only allowed to have 2 variables. So, of course, when we're on this surface, we know that z is 1 minus x squared minus y squared. So I can put that in for z here. Here we go, dA. All right, now let's clean this up. We have the double integral of 2xy plus 2xy plus 1 minus x squared minus y squared, and dA over our region D. Clean it up a little bit more. This is the double integral over D. 1 plus 4xy minus x squared minus y squared, dA. Okay, now the region D is kind of complicated, right? If you once again go back to our surface here, S1, right? X and Y are in this unit circle down here. So you could do this and give the boundaries, described by the unit circle. But of course, this is much easier to do if we just change it over to polar coordinates, right? So we're going to let X equal r cosine theta, Y equal r sine of theta. Theta, of course, is between 0 and 2 pi. And r is between, what is r in between? Is it 0 and 1? Well, let's go back and figure that out. We never really mentioned that. But yeah, if you let z equal 0 down here, if I let z equal 0, we get 0 equals 1 minus x squared minus y squared, which is x squared plus y squared equals 1. So that's the unit circle. So yes, r is going to be between 0 and 1, as is often the case. This becomes the integral from 0 to 2 pi, integral from 0 to 1 plus 4 times x times y. That's going to be r cosine theta, r sine theta, which is r squared sine theta cosine theta. And then minus x squared minus y squared. Notice that we could write that as minus x squared plus y squared in parentheses, and that would be minus r squared. And then times r dr d theta. Okay, so now we just need to compute this integral. Okay, so there's integrating with respect to r. Now let's go ahead and plug in r equals 1 and r equals 0 and subtract. And then finally, integrating with respect to theta, we have 1/4 theta plus, this is a u substitution, 1/2 sine squared of theta, and then now from 0 to 2 pi, and that's going to give us 1/4 times 2 pi, which is equal to pi divided by 2. And that concludes this video lesson.